Section 7.2, example 4, finding the derivative of a parametric curve. Calculate the derivative dy dx for each of the following parametrically defined plane curves and locate any critical points on their respective graphs. Okay, so let's grab this. And now let's take a look at the definition. So the definition of dy dx, dy dx is equal to dy dt over dx dt. So what we're going to do is find the derivative of these individually and then just divide the two, y over x. All right, so let's get that done first. So we have x is equal to t squared minus 3. And let's take the derivative. So dx dt is going to be equal to 2t. All right, there's that. Let's find y. So y is equal to 2t minus 1. dy dt is equal to 2. And now from here, in order to find dy dx, we have dy dt over dx dt, which in this case we have 2 over 2t, which is equal to 1 over t. And there we go. The only critical point is we don't have when this is equal to 0, so we don't have that critical point. The only critical point we have is being undefined at t equals 0. So undefined at t equals 0. All right, so what does that actually mean for the graph itself? Let's try to graph this. So we're graphing it from -3 to 4. So from -3 to 4, let's see. We're going from -3 all the way to 13. 1, 2, 3. All right, so from -3, let's see what x is. 9 minus 3 is 6. So positive 6. So 1, 2, 3, 4, 5, 6. Wrong part. All right, so positive 6 would be over here. 1, 2, 3, 4, 5, 6. So 6, and let's see what y is at this point. So -3 is going to give us -7. So 1, 2, 3, 4, 5, 6, and 7. And let's look at another point. Let's say t equals, or let's kind of find a couple of them. So I'll just pause and graph it, and you guys will see the full graph right now. Perfect. Okay, so this was t equals -3, -2, -1, 0, which is what we had in question here. T equals 0 right there. And all the way down this way, we have t equals 4. So since the derivative gives us our slope, or like our rate of change at that moment, here the slope ends up being undefined, right? Because this is a parabola opening up rightward. And here our slope is going to be undefined because it's like a vertical line right there, which makes sense. I thought that was pretty cool. All right, there's that. Let's take a look at this next one. So part B. I don't think we're going to have enough room for this one. All right, and same thing here. We're going to find the derivative and see what happens from here. So finding the derivative. So for x equaling 2t plus 1, dx dt is equal to 2. Here for y equaling t cubed minus 3t plus 4, dy dt is equal to 3t squared minus 3. And now we have dy dx. That's going to be dy dt, 3t squared minus 3 over dx dt, which is 2. And just to clean it up a little bit, I'm going to factor out a 3 from the numerator and the 2 from the denominator. That leaves us with t squared minus 1. But more importantly, this tells us that t is equal to -1 and 1. So at the derivatives, whenever they're equal to 0, we have a plateau. So it kind of goes up and down. Well, not a plateau, but we have our like either hills or valleys. So it would be 0 here and 0 here, like our tangent lines at those points. So we have that. And let's see what the actual graph looks like. So let's pause this. Let's pause this and see what we have. And done. Wow, love the transition. Okay, so from here, we're starting off with this point, -3. Well, -3, 2. That's when t is equal to -2. And up here at t equals -1, we have this point. T equals 0, we're right here. And t equals 1, we're right down here. And this makes sense. So if we look at our graph, it goes on forever. Actually, when we plug 5 into here, we end up getting 114, which I kind of didn't want to make that big of a graph. So we kind of just throw this little arrow. It does end at a specific point, but I'm not going to draw that whole graph because the rest of the graph doesn't really help us with like our critical values. We only have critical values at these 2 points. Well, and it's when t was equal to -1 here and when t was equal to +1 right down here. So I think that's pretty cool. Again. All right, and let's see. Let's try this last one. All right, so x of t is equal to 5 cosine t, y of t is equal to 5 sine t. Let's take a look. Let's actually graph this one first, just because we know that it's a circle with a radius of 5. So it's not an ellipse because these are both the same. It's going to be a circle with radius 5 here. So let's draw that out really quick. Oh, I guess it's not. I'm not sure what's going on there, but we have 5 here. It's going to be -5, +5, -5 here. At t equaling 0, we start off right here. And that's also t equals 2 pi. So that's those two. We know we go in this direction. All right. And now let's find the derivative and see what the derivative tells us. So we have, let's do that over here. We have x is equal to 5 cosine t dx dt is equal to a -5 sine t. And we have y is equal to 5 sine t. So dy dt is equal to 5 cosine t. dy dx is dy dt over dx dt. So we have 5 cosine t over sine t, or 5 sine t. That's -5. And if we simplify that one more time, so cosine over sine is going to be cotangent t. Actually, before we do that, let's see what that ends up being. So cosine t over sine t. I feel like this, we could use it to like help us figure out our different points. So not our different points, our critical values. So critical values are going to be undefined when sine of t is equal to 0. And let's kind of get that out of our way just to kind of make sense of all of this. All right, so undefined at sine t equal to 0. So when is sine equal to 0? So sine of t is equal to 0 when y is equal to 0, and it's going to be equal to 0 at these 2 points. Let's see, does that make sense? At 0 and at pi. Yeah, it does make sense because we have vertical lines for tangents at those 2 points. All right, so undefined, and our derivative is 0. So another fun fact is 0 when the numerator is equal to 0. So the numerator and denominator are never going to be 0 at the exact same time. So it's 0 when cosine t is also equal to 0. And let's take a look at when cosine t is equal to 0. Cosines are x values, so it's going to be up here and down here. So at pi halves and at 3 pi halves. Does that make sense? Yeah, it also makes sense here because this is when our tangent line is horizontal, aka our slope is equal to 0 at that point. Isn't that so fascinating, guys? All right, if you have any questions, please feel free to ask. Otherwise, bye.